Woohoo! It's a great day to learn some pre-calculus. I'm Miss Leg Battles, and I'm here today to talk to you about dot product. Our objectives today are to find the dot product of two vectors, to find the angle measures between two vectors, and to use the dot product to determine if vectors are orthogonal. Don't worry if you don't know what orthogonal means. We're going to get to that. So before we begin, I wanted to talk to you about the difference in what vectors look like when we denote them in print versus when we write them. So I know you may have noticed in my notes the way I write them, but then also the way they're denoted on your online assignments. So here, notice that the vector is written in bold print. The bold print V, the vectors 3i plus 4j, or the V and I and J are all vectors, but when I write them, I often write it this way. I'll put this on top, and that means vector. But sometimes you might see it written this way. Looks kind of like a ray in geometry, but you know, a ray goes on forever, but a vector does not. And then also sometimes you see it with like a little hat on like this. So any of these, the little part of an arrow or the little top hat here, any of those in writing could denote a vector. But when you see it in print, they're just going to be in bold print. So off to our first objective, to find the dot product of two vectors. First of all, I want you to note that when we find the dot product of two vectors, we get a scalar, a real number, not another vector. When we added vectors, we got a vector. When we subtracted vectors, we got a vector. When we multiplied a vector times a scalar, we got a vector. But when we do this dot product, which is not really multiplying, but finding the dot product, we do not get another vector. Now, notice it says if vector V is a sub 1i plus b sub 1j and w is a sub 2i plus b sub 2j, then the dot product is defined as a sub 1, a sub 2, that's that product, plus b sub 1 times b sub 2. So the dot product of two vectors is the sum of the products of their horizontal component and their vertical component. So let's get right to an example. First, we want to find the dot product of the vectors v and w, and then the dot product of the vector v with itself. So this is number 3 in our text. So what are we going to do? I've copied our formula down. It's a1, a2 plus b1, b2. So that's going to be 5 times negative 2 plus negative 4 times negative 1. And that gives me negative 10 plus 4, which is negative 6. So the dot product of v and w is negative 6. Next, we're going to dot v with itself. So I would have 5. That is my a1. Well, we're using a1 again, so it's going to be 5 times 5 plus negative 4 times negative 4, which gives me 25 plus 16, or 41. So when I dot v with itself, I get 41. Now what I'd like for you to notice here is that when we dot a vector with itself, we get the square of the magnitude. Remember, the magnitude of vector v is given by the square root of a squared plus b squared. So when we dot v with itself, we get a squared plus b squared. Let's look at another example, number 8. If v is the vector I and w is the vector negative 5j, what is the dot product? So I've written our formula down again for the dot product. So let's just substitute in. It would be 1 times, now there is no I component in W, so that's just going to be 0 plus 0, because there's no I component there, times, there's no J component in V, so it's 0, then times negative 5, that's our B sub 2, or our J component in W, and that gives me, well, 0. So the dot product of V and W is 0. Now what do we get when we dot V with itself? That would be 1 times 1 plus 0 times 0. Remember we talked about that in the previous example. We have the square root of a squared plus b squared, which in this case is 1. Now let's look at number 12. For this problem, we have 3 different vectors, and we're to find v dot u and then add v dot w. So let's see what that would give us. V dot u, that would be 3 times 2 plus 1 times negative 1. And then we're going to add to that this other dot, which would be 3 times 1 plus 1 times 4. Now, when I simplify, I have 6 minus 1. Here I have 3 plus 4. So when we add those together, we have 5 plus 7, which is 12. Let's look at some general properties here of the dot product. First of all, notice that u and v are vectors and c is a scalar. U dot v is the same as v dot u. Also, u dot v plus w is the same as u dot v plus u dot w. So it looks like our dot products act very much like some other properties that we know about. Number 1 looks like the vectors, the dot product is commutative, just like multiplication would have been. And on number 2, it's distributive. We have our property of 0, but notice on number 3, the first 0 is the 0 vector. The 0 vector times v, the vector, is 0, which is a scalar. Now, number 4 is the one we just talked about. When you dot a vector with itself, you get the square of its magnitude. And then on number 5, notice it really doesn't matter the order in which you take the dot. Our next objective is to find the angle measure between 2 vectors. Notice we have an alternative formula that comes from the law of cosines. It takes a little bit to derive this, so what I've decided to do is just give you an idea about why this comes from the law of cosines. If we let these represent the 2 vectors v and w, and then this is the angle between them, notice if I finish this out here, made it into a triangle, this would look like side angle side. Side angle side is a pattern where we would use law of cosines. So what I want you to notice here, that if we take this alternative formula that comes from the law of cosines, this is an alternative way of finding the dot product, we can solve it for cosine theta. Notice if I just divide both sides by the magnitude of vector v times the magnitude of vector w, if I do that on both sides, what happens? Well, this divides out and I'm left with cosine theta equals all of this. So that's exactly what we have down here in a formula for finding the angle between two vectors. So if we take this form here, cosine theta is the dot of v and w divided by the product of the magnitudes of v and w, and we solve for theta, we just need inverse cosine. So let's look at an example of that. We want to find the angle between vector v and vector w and round to the nearest tenth of the degree. Now we're going to let theta represent that angle between the vectors. So I have two vectors here, v and w, and I've copied down my formula for finding theta. For organization's sake, let's just come over here and find the dot product. First thing we're going to do is find the dot of v and w. So that's going to give me negative 2 times 3 plus 5 times 6. So that's negative 6 plus 30, which gives me 24. So that's the first thing I need for my formula. Now, next, we're going to need the magnitude of v. So the magnitude of the vector v is, of course, the square root of a squared plus b squared. So that's the square root of negative 2 squared plus 5 squared, which is the square root of 4 plus 25. That's the square root of 29. Now let's find the magnitude of vector w. That's going to be the square root of 3 squared plus 6 squared. So that's the square root of 9 plus 36, which is the square root of 45. Now, I'm going to take all these three things that I found, and I'm going to substitute them into my formula. Now, what I want you to notice is I'm not going to round off each of those values. I'm going to substitute them in as they are. Remember, I like to say YOLO. You only round once, so we can't round these off and then plug them in and round off again. So this is just going to be the inverse cosine of my dot product, which I found to be 24, divided by the magnitude of vector v, which is the square root of 29, times the magnitude of vector w, which is the square root of 45. And when I put that in my handy dandy calculator, I get that theta is about 48.4 degrees. 48.4 degrees. Check that in your calculators. For our last objective, we're going to use dot product to determine if vectors are orthogonal. I told you at the beginning that I would make sure you know what orthogonal means. Two vectors are orthogonal if the angle between them is 90 degrees. So if we were talking about rays or lines or segments, we might say they're perpendicular, but orthogonal is the word that we use for vectors. Now, I want you to recall the alternative formula for the dot product. I have it written here. So in this case, theta would be 90 degrees. So if we put in cosine of 90 degrees right here, we know that cosine of 90 is 0. So this value goes to 0, and 0 times anything is 0. So we end up with 0 for the dot product. So what we need to know is that vectors are orthogonal if and only if their dot product is 0. Maybe we should write that. Really, what we're using here is if vectors are orthogonal when their dot product is 0. In other words, if the dot product is 0, then they're orthogonal. but it really could be written as a if and only if statement. We find that it goes both ways, so let's write that. Vectors are orthogonal, means forms right angles, if and only if their dot product is 0. You know, this is important in a lot of cases. One study, like when we're using force or projection and we need the vectors to be orthogonal, this is when we're going to use it. I mean, if we're going to shoot pool, if you know anything about billiards, that's all about vectors, and we need to understand about vectors being orthogonal. I hope this has been helpful to you. Oh, wait a minute. I have another example. We just told when, what makes vectors orthogonal. Let's work one out. Let's take this off and start all over. Use the dot product to determine if the vectors are orthogonal. So I have two vectors here. So what I want to do is take their dot product. If their dot product is 0, then they're orthogonal. And if it's not, then they're not orthogonal. So that means V dot W, using my formula, that would be 1 times negative 1 plus 1 times 1. That's going to give me negative 1 plus 1, which of course is 0. So yes, that means yes. Vector V and vector W are orthogonal. Now I'm ready to say bye. Hope this has been helpful. I sure miss seeing you. It was a great day to learn some pre-cal.